We have a full room, which means I get to start. Whoever's late, too bad. Welcome to the first TCN event of the 2013. It looks like we have a very big amount of interest in today's topic, so the speakers should be very nervous. Are you nervous? No, sorry. I just wanted to make a few announcements. First of all, the next event is going to be in February 25th. It's going to be yet another TCN talk about TypeScript, although the first one where it's actually had the name TypeScript. So there's something new. Actually, there's plenty of updates. We've launched TypeScript and had a lot of interest in it across the board from all over the industry, and lots of things have happened in the language as well. So I have on here that we have Jonathan and Anders and Steve and Luke give the talk. Is that still the plan, to have all four of you give the talk? Quite possibly. Okay, so there's going to be 4 speakers. Okay, there should be an invitation going out pretty soon. Shortly after that, we have the Mind Swap, the TCN Mind Swap, which is a yearly all-day event with lots of talks. I think, is it only open to the sort of full members? We don't know. Okay, we'll find out. We can't remember. So it's an all-day event of shorter talks. We don't have all the talks lined up yet. I think a lot of you should have already gotten the invitation for talks. So if you still if you have something you would like to talk about in a slightly shorter talk to a large set of people that's language related, please respond to that email from Nicholas. I think he'll send out a reminder tomorrow as well, just to get you guys out of the woodwork. We would like to fill up the day with interesting talks. I think that is it for events. Please remember to fill out the online surveys so we can see how we did, and just to make the speakers more nervous. We normally ask you to speak into the microphone, but I think we have enough speakers that we don't have a microphone left for the audience, so we'll just ask the speakers to repeat the questions as we go along, because this is being recorded. I also do want to remind you that there's a mailing list that any FTE at Microsoft can sign up to and get reminders about these events. And most of you are probably on it since you're here. But do keep thinking about, are there people in your teams around you that would have an interest in learning about language topics, and just go sign them up. Don't ask them, just sign them up. So, and food at the back there, if you're a first-timer, you'll know that the food runs out quickly. So, or if you're not a first-timer, so please go and help yourself. And other than that, I think it's over to Joe and to Jared and to Alex to tell us all about what's going on in Midori and its programming language, which I think is still called M#. Is that right? Well, they're thinking about it. Suggestions welcome. Okay, thank you very much.
I know over 50% of the people in the room, but so my name's Joe Duffy. I work on the Midori team. Most of the talk today is about the programming language we use, but I am going to give a quick overview of what Midori is, in addition to a kind of a quick status update, since we've had some exciting achievements in the last year. And I also have Jared and Alex here, who are the primary developers on the language compiler itself, and definitely the experts on the kind of the features they're going to talk about. So first, kind of what is Midori? It is a new operating system. It gets started around 2007. Eric Rudder, Chris Broom kind of kicked off the project, and the goal was to solve a bunch of hard problems facing the company in a no legacy kind of way. So they explicitly didn't think about ship vehicles. It was really more of a research with the idea of transitioning into incubation someday, and then eventually transitioning into a product that would influence what the company actually does in our commercial offerings. And so one of the main bets, and started with looking at Singularity, the work that was done in MSR from Jim Laris, Galen Hunt, and those guys. So it is written all managed code, so you get safety. But one of the keys was we really wanted to deliver native code performance. We wanted to be competitive with platforms like Windows, on server, on client, across all sorts of different devices. And one of the key things is really having type memory and concurrency safety across the entire system with no ability to opt out. So that includes device drivers. It includes even the garbage collector compiler that runs in the kernel and a lot of the kernel itself. And there are some other aspects that are interesting around resource management that are very different from Windows. Having strong isolation, not doing demand paging, which a couple decades ago would be completely unthinkable, but we find actually the ability to read memory and knowing that it's not going to do I/O actually leads to better performance in a lot of interesting scenarios. And really wanted to get ahead of a lot of disruptive trends around heterogeneity and actually running efficiently on small devices like ARM. I think so there's a technology which is a fairly radical thing, but the other radical thing I think that I actually love most about the project is the unique culture. It is a lot different from other product teams at Microsoft. It is very different from MSR. It is all developers. Everybody writes code on the team, even managers. I'm actually a manager of managers, and I try to spend as much time as I can writing code. And another great thing about the project in my mind is we build the system on itself. So when we develop a new language feature, immediately it's being used up and down the stack. So when we talk about some of the features we're talking about today, like immutability, for example, we're actually using that in the web browser, in the some of the stack allocation we're actually using in the runtime. So the system itself is kind of built to be self-consistent. And Eric is pretty adamant about, hey, this feature, I don't believe it until it's actually used throughout 100% of the code. And I actually think that's a great way of getting kind of iterative feedback. I think actually we should do that throughout the company a bit more. Because you don't find out late in the game that, hey, we didn't quite get this language feature right, and now it's too late to fix it. We actually find out very quickly. And despite being research/incubation, we do have a very strong engineering culture. So there's many areas of the project where people are just passionate about getting 100% test coverage. Certainly not the entire project that way, but we run days and days worth of stress, and it really is kind of like building a product. In fact, I think the engineering culture is a bit stronger than some product teams I've actually worked on at Microsoft. And finally, all of the code, with a few exceptions I'll note, is actually written in Midori C#. So Matt's called it M#. We're trying to kind of brand it as just a flavor of C# rather than an entirely different language. That's why I've taken to call it Midori C#. But that includes the kernel GC, file system, drivers for USB, 10 gig NIC, HTML5 compliant web browser, web server, you name it. The exceptions I will note are the system is built on policy-free microkernel written in C++. It's actually very small. We are reusing components from across the company as well, such as the Red Hawk GC and the JavaScript engine. So Midori C#, since we started with Singularity, we did start with Sing#. And at some point, we kind of moved away from that, moved to C#, tried to use libraries instead of the language in many areas, and we added a lot of static analysis through fxcop and other tools to check. From the start, we took a stance on no reflection, no dynamic, optimized ahead of time compilation. Again, this is the managed code safety with native code performance. We soon kind of hit the limits of where we felt, a hands-off language design could go. We found, a lot of things were in fxcop that really should be in the type system, and it would become clunky. The programming experience wasn't as good as it could be, and some of the radical ideas we had, you couldn't do that with fxcop and attributes. Or if you could, it would be quite ugly. So I actually joined the team in 2009 and kicked off Midori C# very shortly after that. In fact, Eric wouldn't allow me to, but I did it kind of in my spare time, and then finally it was useful enough. He said, okay, go for it, and then the camel's nose was under the tent, and here we are today. So it is based on the C# compiler code base. It's not based on Roslyn, so it's the kind of legacy, if you will, C# code base. But it was great because we could reuse a lot of the tests and everything, make sure that we were starting from a solid foundation. We started with incremental improvements. So awaits was actually the first feature. And this was actually around the same time that C# was developing awaits. And we kind of actually contributed some ideas and code back to the C# product team as we did this. We then slowly innovated a bit more, added immutability, and we stuck to kind of additive and compatible as our mantra. And recently we've kind of decided, hey, you know, it's great, we're optimizing to make porting C# code easy, but at the end of the day, the resulting code wasn't taking full advantage of all the features. And by changing some defaults and twisting things around a little bit, we could get more value. And so that's where we are now. We're just starting down that path. And we definitely try to mimic the C# design team, very successful with the note structure and the design team structure. So we've got a bunch of people here. The main code contributor, the only person not speaking today is Sean Katzenberger, who actually, if you look at the C# code base, his name is all throughout the code, so he's highly qualified to help with the design and the implementation, so that's been a great addition as well. So quickly, Midori status. So where are we? So I said it's kind of research incubation. Well, in 2011, we had a review with Steve B. and Chi, and they said, hey, this all looks great, but before we believe it, hey, why don't you work on getting a real workload in production? So we had already been speaking with the speech recognition team actually for some time because they struggled with scalability, throughput, and safety. And so it was a natural choice, and they were a great partner. So we said, okay, let's go forward. It took us about a year to get their 500,000 lines of code written in C++, ported over to Midori C#. Some nice simplifications along the way, so it ended up being 300,000 lines of code at the end of the day. And we got our first production request served roughly a year afterwards. So right now we're taking about 15-20% of the Windows Phone traffic, speech recognition traffic. So actually, if you talk into your phone right now, it will hit the Midori servers because all requests in this that go to the front door that serves this geographic location actually go to Midori. And we've served over 20 million requests at this point. The great news is you see half a second to 1.5 second less wait time. So when a user speaks, you know, from the time they stop speaking until they get the response. And we've increased the throughput and capacity of the data center by 3x. Remember, this is all safe code, and we started with a C++ code base. And really, a lot of this is a testament not only to, you know, the optimized compilers, the programming model, but also the architecture of the operating system. We see, because speech is so compute and memory bound, actually good locality matters a lot. And the architecture of Midori, because there's lots of small communicating asynchronous processes, actually contribute a great amount to improving locality. And just a reminder, you know, we're not just focused on server. We still kind of are chasing the general purpose OS stream, including, you know, running on ARM laptops. We do have a full UI stack based on reactive programming. We have actually several guys from the browser team here today. So the way I describe it to people is we're kind of NT circa 1992, right? They're focused on server, doing a great job at that. Eventually, Windows 2000 comes. It's a ways down the road, though. And finally, we are tracking to kind of Midori V1 release, including stabilizing Midori C#. So what you see here really is what we expect to be in V1 of Midori C#. So the talk today, which we should get to quickly, I've chewed up way too much time. The first, there are these kind of 3 major feature areas. One is the immutability and isolation features, which we call taming side effects. Another is the features we need for efficient systems programming. And the final is the error model that we use in Midori. So with that, I'll hand it over to Jared, who's going to get started on TSE.
This is working? So, for those of you who don't know me, I'm Jared Parsons. I think I've worked with, like Joe, probably about half of you. My history, I started Microsoft in DevDiv. I worked on the languages team in the core of Visual Studio for about 5 or 6 years or so. And After spending all that time sitting in the bowels of Visual Studio trying to fix other people's random multi-threaded bugs and all kinds of comm issues, eventually I gave up and decided that, quite frankly, people are too dumb to write multi-threaded code, self-included. And the big problem is just unintended side effects. No matter what you do, no matter how you structure a code, either you don't quite understand what's going on under you, or the next guy coming didn't understand your variance, and eventually you will destroy the model. So the principles we've started out with is, like we said, we have embedded the notion of side effects into our type system. So these are very visible, very compiler-aware things. And the other big one we have is we do not allow mutable statics in our system. We do allow statics in general, but they must be read-only and immutable, and that's the default, and you can't change it. There is no untracked state in our system. So things like file.open, that doesn't exist in our system as a static method. We use more of a capability model. If you want to open a file, you're going to need access to the file system capability. If you want to, I don't know, get various timers and performance information. Once again, this is all a capability-based model. So no global mutable state. It's really lovely. So the goal for all of this is we really want to enable safe concurrency in our system. So like we said, concurrency is one of our fundamental goals, and we achieve this by tracking side effects. So, and also in general, just having the ability to control side effects gives you much more control over your code, much more control over what people can do with the objects you give them, and leads to a much more correct model. So, like I said, this is functional code when desirable is kind of our motto. Midori C# in many ways, the way we design this is it's kind of a superset of C# at the point. You can take C# code, and as long as you don't have mutable statics, you can compile in M#, and it works. We've made very few changes to the language because we wanted to have a very fast uptake into the Midori code base. As we said, we have 4 million lines of code. Massive breaking changes would not have been conducive to porting. So, like I said, we now have 4 million lines of code roughly, and it's all TSC enabled, and side effects are tracked. And now we're going to get to what it actually is. So the basic way we track side effects in our system is by annotating object references with permissions. We have 4 basic permissions in our system. So writable is the unstated default. If you have a reference and you state no permission, you get writable. And so this feeds into our idea of we want to be C# backwards compatible. So state is mutable by default. Readable restricts an object to non-mutating operations. It is a query thing. And you might look at this and think, oh, C++ const, this is very different. Readable is deep. The entire transitive closure of objects that are reachable from this reference cannot be mutated. Any call which involves only readable input will never change the state of the system. It can query only. Immutable is simply a stronger form of readable. The actual definition of immutable is an object graph which has no writable references. So this is a fully provably immutable structure. It will always give back the same information, and it can never change. And then for very interesting, highly generic scenarios, we do have the idea of parametric polymorphism in the system. So you can encode permissions as a generic parameter. And you can now in our system have type parameters or permission parameters. And this gets pretty interesting when you get into some deeply generic code, but large and far, most people never see a generic permission. It pretty much exists at our core layer and in none of our applications. The way we model these is a subtyping relationship. So readable is the least permissive permission in the system. So both writable and immutable references can convert to readable. And what this means is in our type system, instead of having object as the top, readable object is the top part of our system. Anything can convert to readable object, much less can convert to writable object. And so when you actually see this in code, so nice standard simple class. So you have person with 2 methods, a mutating set name. The way we control access to the object is we put the permission just after the method. So you can see here we have a readable and a writable method. The first method has no permission, so it's default of writable, and you can do whatever you want. Second method, though, is readable, and so you can only query state about the object. If you try to do something like write to a field, the compiler is going to scream at you if you try to call other writable methods. Likewise, the compiler is going to get a little bit upset with you. But simple query methods work just fine. The same applies on the receiver side. Down here we have a local which is annotated as readable. So querying for the name of the local is just fine. But if you try to do something like call a setting method, it's great. And like we said, these permissions are deep. It affects the entire graph. I'm completely assured that p1.getName does not mutate the state in any observable manner. So up until now, people might look at this and still say, it's C++ cons. What have you guys done? Not worth anything. Where it gets more interesting is when you have complex objects, so collections. Collections are very interesting because they have layers. If you look at this, there are really two things that are interesting to protect in this system. One, you want to protect the contents of the list. Can someone add or delete from my list? Can they change it? Or two, can they mutate the things which are already inside of that list? So here, this is, like I said, it's an unstated permission. This is a fully mutable list. I can add new people to it, and I can grab particular elements of it and mutate them freely. Now, though, what we can also do is constrain the list to be a readable list with writable elements. And what this means is the contents of the list now cannot change. The receiver of this object, they cannot add new people to it, they cannot clear it, they cannot remove items. But they are completely free to grab people out of that object and mutate them to their heart's content. So you cannot change my collection, but you can mutate the people inside of it. And one of the real fun things to note is see the assignment up there? List 2 can accept list 1 as an allocation-free assignment. The permissions in our system, they basically have a form of variance. In the same way that you can assign a writable object to a readable one, it's okay to assign a writable collection to a readable version of that collection. And this works, it's alloc-free, it's just fine, and it's verified by the type system. And you can take it even further and say, I want to go from a readable collection of writable elements to a deeply readable list. You can't change anything, here's a collection of people, you can query it if you'd like to. And once again, it's an allocation-free assignment. When we allow basically any assignment which is less permissive than the source, it's allocation-free, it's legal, it's checked, and you can't do diddly with it. You can still query the people and look at them, but you get readable objects out of there, but you can't mutate the world. And so the change in collections is really nice. One of the big advantages to having this state where we can kind of tweak collections in various areas is you find that a lot of the collections in your system, you just don't need them anymore. So we have our own version of read-only collection, read-only map, and things of this nature. They're not valuable at this point to us. And we've been basically deleting them because they're simply an extra allocation overhead for something we can express allocation-free in the type system. And what's the other good one is we like arrays again. It's nice little fast, efficient structure. Because you can control what people do with it, suddenly you find like you had all these read-only collections, you look at it, they allocate a fixed-size array, they put 10 elements into it, and then they wrap it in a allocation wrapper. So you have the overhead of assignment, you have the overhead of access. Now we just pretty much freely pass a readable array of writable elements all through our system. It's very nice, much more efficient. And if you look at, I wanted to throw up here map because it's a little more of a complex one. We don't really have enough time to dive into the generics today, but I wanted to show you like the skeleton of what our collection types look like in the system. As you can see, this, the API is not too much more different than you would expect. The big differences is you'll see like count, keys, values, these things are marked as readable to basically say they're non-mutating. Getting a value out of the collection is not readable, is a readable operation. It can't mutate, it'll all give it back. And you can see we're guaranteed we can't mutate the keys. Same with contains. Contains is purely readable. It's very nice. The only thing that might kind of strike you a little odd is these little contains words up here on the type parameters. The reason we have these is, as we said, we've designed M# to be more of a superset of C#. And so everything in the language at this point is opt-in. And so, as we showed before, the ability to change permissions and move to less permissive layers, it does have a subtle effect on what you can do with generics. And hence, we make you opt in to this. And you have to explicitly state, I want to opt into this particular feature. The good news is, though, the vast majority of our system opts in because it's awesome. It's not very much work at all. And as Joe said, default changes are coming. So up until this point, we've talked about readable and ability to constrain, but what everyone really wants is immutable objects. Stuff that can't change is nice. So creating an immutable object in M# is quite straightforward. As you can see, an immutable person equals a new person with, a new name and a new age. And there's nothing special here. There's no tricks going on behind the scenes. I didn't redefine person in any special way. Pretty much any standard person type you've authored in C# today would compile with this expression and be provably immutable. And the reason we can do this is, once again, it gets back to our goal of no mutable statics. Since we have no mutable statics, we can look at this new person expression, and we know that that is an isolated object graph. You allocated a new expression. The only two pieces of data that went into it is a string and an int. They're both immutable. There is no writable reference to that object graph except for the one that's returned from that expression. That is the only writable value left in the system. If we choose to view it as readable, that means there are no writable references in the system, and it is by definition an immutable value. And what's really nice is person did nothing. This is just a standard .NET object, and we can create it freely as we want. This also works for collection types. So you can also say an immutable collection. It works for pretty much any object. Do standard initializers. The code that you write in C# today just works. Now, we do recognize that sometimes more complex initialization is required. A lot of immutable objects aren't built up in just one statement. A lot of times you want to collect this set of values, build them up, and then eventually convert them to immutable. And we have a couple of different ways of achieving that. The first one is we have a lot of helper methods, which you see immutable create here. It takes a lambda. You can slowly build up your object, and then it will return it as immutable. And we'll get into how the delegate works in just a minute, but at a high level, we can, in addition to being able to constrain references, we can constrain delegates. So we say the same things, and a delegate is immutable. You can't capture any mutable state, and hence we know that anything that comes out of this delegate is also going to be immutable because there was nothing for it to capture. So, as we said before, this whole new person expression that comes back, this idea of this is a self-contained object graph. We actually represent this in the type system as well, in what we call isolated values. So an isolated value is one which has no external mutable references, no aliases. It's in some ways a linear object, just a little more usable. And the idea is, what we can say is we have an isolated list of people. And the whole idea with isolated is we have an object, it is mutable, it's completely writable, you can add to it. But what we know is this is the only reference to that object graph. There is one external reference. The object graph itself can self-referential all at once, but the people builder itself is the only external reference. And so now, because what we can do is, since it's still mutable, we're allowed to freely mutate it. We can call the add method on it, and we can pass in other isolated graphs of object. So we have an isolated graph in person builder. We create a new person. It's another object graph with no references. And we can freely merge these two object graphs together into this single reference. And what's nice is these things can be passed around. You can store it in a local, and we have mechanisms of transfer, which we call consume. What consume does is consume is an operation which both reads the original source reference and destroys it. So it is a value, it basically pushes the value on the stack, nulls out the original one, and returns it to the caller. So it's a true linear handoff of the value. And so what we can do is, Yes. Yes. Any storage location you can do. You can do array elements, you can do fields, locals, what have you. Exactly. You can make anything that has a, I can't remember in the CLI spec, but, oh, no. Perfectly fine. And so what's nice about this is, before in the previous slide, we showed kind of the progression of more complex immutable objects. One-liners, multi-liners, but you're still in the same method. When you have isolated values, you now have the ability to pass them between methods. Because one guy can create an isolated value, put a few elements in the list, and then hand them off to the next method. And this can continue on and on. People can build these values up slowly until they're ready to freeze the object and say, this is it, we're done. We want to see this now as immutable. And at any point in time, when you consume an isolated reference, it's the moral equivalent of saying new person. You've deleted the one reference to it in the system. It is now an object graph that has no references, and you can do whatever you want with it. You can convert it to writable, you can convert it to mutable, or readable. It's all completely safe, and we use this pattern pretty heavily in our system. It's a very easy pattern to pick up once you get going, and we pass plenty of isolated values around that make very complex object graphs, which we then can freeze and then pass around to wherever we want to. And as we said before, with that immutable create, we kind of brushed over the fact that there was a delegate there, and could it be capturing bad things? Delegates, in the way that you can constrain methods and references, you can also constrain delegates. So just as you put the permission into this after the method, you do the same thing with delegates. And what's really nice about the delegates is the permission constrains what the implementation can do. If you have an immutable delegate, it means that the operation will execute immutably. It will always return the same value. And this affects, on the lambda side, it affects things like capture semantics. If you are binding a lambda to an immutable delegate, you can only capture a mutable state. And so that means if you're trying to capture a local, it must be immutable and it must be read-only. And same with fields or objects. You can't capture anything that could ever change. So an immutable local will always produce immutable values no matter how it's bound. We do also allow for readable captures. They're a little more restricted. You can capture writable values. You can just only do readable things with them. They're actually very prevalent in our system. I mean, can you imagine one of the big problems you have is if you've ever seen an example where people will do a parallel for each where they try to sum and they start mutating all kinds of external state in their callbacks. If you have a readable delegate, can't do that. It'll smack you down for trying to do your mutations, and it's a nice, provably side effect-free item. Ugh. Yes, and you can see here in this example, we have our async factory run where we're taking this pure func, which is immutable, and attempting to capture anything from A here is going to fail because this is a mutable value and it's not read-only, but we can capture freely from B here because it's read-only and immutable, so this will always return the same value. Nice, and thanks. So, like we said, we didn't, somewhat short on time today, so we couldn't cover all of TSC, but it's kind of the high-level view of TSC. And as I said, we've turned this on in Midori now. It's roughly 4 million lines of code. It took us about 1.5 years to do. A lot of that, though, was iterating on the model. Really, it took us probably about a little over a year to get to a model which we feel comfortable with can express all of the, basically, rigors of a full operating system and web browser and what have you. After that, it took us about 4 months of hard porting to get us all there. Along the way, we found plenty of bugs, many places where people were subtly mutating immutable values. Because like any other system, we have all of these values which are commented as, don't touch this. You can't change this, but follow it through enough layers and you find someone who's mutating it. As we ported, there were a couple of reoccurring pain points as we try to push this through the system. The first one was for the language team was generics. It took us 4 different models to get generics the way we would like them. Some people on our team can attest to the problems we had in the first few. But now we're very comfortable with the model. It actually has been it's a very flexible model. We can do all the nice things we want. The biggest problem in our system continues to be mutable statics. People love them. They're convenient, they're easy, and they're dangerous. And so as we turn Midori on in the system, we find plenty of these, and we have to work pretty hard to get rid of them and either switch them to truly immutable data or more of a capability model, depending on where we are in the system. And the other primary driver, as we said, this is mainly a backcompat language. So when we turn TSC on a given project, we get hit up on 2 things, mutable statics and other places where people are doing something like contracts. We do have contracts, and I was going to explain them in detail, but we don't allow our contracts to be mutating. So if you had like a debug assert or release.assert, we assert that they're side effect free. And so you turn that on, and so you'll find people who had marked certain methods as like get count, then you have to go mark that as readable, and then go and find all the methods that call and mark them as readable too. And what you find sometimes, though, is that people, all these getters methods, they actually are mutating state. And people's expectations don't always meet up to reality. I have had several people report a project, and they're like, why didn't you make this more restrictive? Why do you not make this readable? And it's like, well, because it's not. And it's very funny to actually, the compiler is a ruthless enforcer of its principles, and so it very often surprises people. So it's been a little over 2 years since I joined the team. We're really happy with where we've gone. In addition to getting everything ported, we've also started to take advantage of this in our system. Parallelization is on the forefront, but one big notable win we've had with this is our statics are provably immutable. And so what we now do is actually at compile time is we freeze all of the statics in our system, much in the way that C or C++ would do. We basically run the compiler, the backend compiler at compile time, run the statics, take the object graphs, and write them to read-only memory. Because we know we're never going to mutate them, we can put them in there, and we take all of those static initializer code that used to kill startup perf, and it's gone. It is now, those type initializers go away, the mutables are frozen. It's quite lovely. The other big problem we have, though, is, as we said, the way we've ported this code is we turn it on, we fix the errors, and we say, we're done. The problem, that if you look at code, though, we're only marking things as non-mutating if we have to. If you go and logically look at code, though, methods which do not mutate state vastly outnumber those that do. But our code is kind of inverted at the moment. We have many more writable methods than we do readables. And so one of the things we're looking forward to is we're actually going to flip the defaults at some point in the near future and make non-mutating methods and potentially non-mutating references the default in our system and force people to explicitly annotate everywhere a mutation occurs. Early on, one of our kind of metrics was lines of code, like how many annotations do you need for lines of code, and that's not going to be as important when we make that change.
One common strategy, if you have big, observably mutable for instance, is depend heavily on caching for the efficiency. And it seems like you ruled out caching in some ways really are not doing anything.
Yay. Someone asked. Happy.
Working for that?
Yes. Yes.
Maybe later.
So as for the people on camera, Mads was asking if it's, we've done a really good job here of representing physically immutable data, but what we have not explained is how do we represent logically immutable instances. So just like C# has the unsafe keyword, we do have this nasty thing in our language called unstrict, where you can say, Jared's an idiot, and you can just do whatever you want. We do not expose this to third-party code, though. This is limited to, there is a compiler option to enable it, and we only enable it in the low parts of the system. And we do allow cheating at the low levels of the system. So there are certain things, like we do have a lazy type. And what we do is there are certain primitives where we say we're going to cheat, but we're going to sit down and make sure it applies to the greater rules that we have for the language in the system so it can't violate safety. And for things like lazy, the way we enable them is we give you a delegate, but the delegate is not writable. You can't mutate state in it. You can query state and produce a collection based on the available inputs at the time, and so it will be eventually seen as writable, but in your lazy operation, you cannot mutate state. And so we can use unstrict and be very certain that you are not violating your system, but we can add these convenience little tricks at the bottom. And we do have a few of those. They're very limited in number. We actually thought we'd need a few more of those than we ended up with, but we do have them at a low level because, yes, you do occasionally just want to cache something. So going to kind of switch gears here for a minute and talk a little bit more about systems programming because at the end of the day, Midori is an operating system and perf is really important. So we do have, Midori has a very deep async model in it. Midori is a completely non-blocking operating system. Like, by all the nice stuff that Windows 8 added, we do that and with a lot more rigor. It's not, if it will take more than a few seconds, if you touch the disk, you touch I/O, it is awaiting. So methods have to declare their ability to allow interleaving. So if you're going to await in a method, await is very much like C#. Your method must say that I do interleave. It must declare awaits, and then you can await a specific value. And attempting to call a awaits method, if you were to try to go await socket.connect and you did not have awaits there, it would actually lead to a compilation error. And so this is how Midori's worked for a long time. This is one of the first things I turned on when I moved there. And much like C#, we started with a continuation passing system. So you compile Midori, you look at it, and there's thousands of state machines that are continuation passing, throwing things in the heap. It's a lot of fun. Eventually, though, what we have gone to now is it worked, but the performance just wasn't good enough for us. So now our await system is actually implemented with coroutines. So the beauty is, I missed a slide, sorry guys, but when you compile this now, the way the connect method looks in IL is just delete the 2 keywords. Like there is no state machine. When you call an awaiting method, we're not like throwing a task in under the hood, none of that. Like if it returns an int, it returns an int. Like there is no state machine. The backend compiler guys love it because then they can optimize the crap out of our methods. And so our awaits are 0 allocation. It's very nice. A couple of other things we do in the system. We do allow for by ref returns and ref locals. This is very handy. It's very similar to Red Hawk's model, except we only allow like provably items in the heap to be returned as ref locals, just for simplicity of the model and implementation. And another thing is, for a long time in Midori, like when I first got there, there were lots of abstract classes, and I tried to add some interfaces and got a lot of nasty grams, because interfaces are just not efficient. Every call requires looking up the V table, then the dispatch call. And for a long time, interfaces are highly avoided in Midori. But one of the really nice effects of our programming model is because we do not have to worry about multi-threaded writes to the same location, since it's all provably safe, is we can represent objects as 2 pointers safely. We don't have to worry about tearing problems. And so what we do for interfaces now is whenever you declare an interface local, under the hood, we actually have 2 different objects. We put both the object and the V table, or in the interface table pointer next to it. So interface calls, instead of doing 2 lookups, are just a virtual call. It's just, here's the table, here's the pointer, go. And as you can see, we have a nice little table down here about what the relative speed is between virtual calls and interface calls on Midori and CLR. And Midori interface invoke now is actually the fastest of all 4, with virtual calls being just ever so slightly slower. And you can see they're almost about 2/3 the cost of the CLR interface invoke. And so it's a nice big win for us, and I can use interfaces again, so I'm really happy about that. The other one that we've done is our delegate class, our delegate types are value types in our system. So method groups, allocation free. It's very nice. We can pass delegates through with a lot less overhead. And once again, we do a trick. They're just 2-word structs, but because we don't have to worry about object tearing, we can do this, and it works very nicely. And I think oh, yes. Oh, and now you guys get to meet Aleks. Oh. Do we have co and contravariant delegates? So the question is, do we have co and contravariant delegates? And the answer is not right now. So good catch. Yes, because the ability to have co and contravariant delegates does get affected by this. Our system we have changed the generic type system in a very subtle way to allow for it. And we will, our plan is eventually to turn on covariance, and it will still be legal in delegates, but it's...
Yeah, so we will have co and contravariance for V1. What you might be getting at is that it's a transforming conversion now. So say even for interfaces, right? Because it's a different kind of the double pointer, you actually have to perform a transforming conversion when you do a co and contravariant conversion. And so for generics, we actually have new constraints. So like where T colon class is kind of different from what it means in .NET, because it doesn't mean you have atomic conversions between these. And the representation is different for an interface versus a class as well. So what do we call it atomic now, right?
We call it atomic.
Where T is atomic. But.
Uh-huh.
So it seems that with your model, one of the sort of things we occasionally enjoy with the C# model is that you have a separation, a possible separation of the initiation of an operation from the consumption of its result.
Mm-hmm.
You pick it up, you hold on to the task for a while, then you await it.
Yeah.
It seems that you don't have an abstraction, a first-class object you can do that with here.
We absolutely do. So we do have an abstraction. It is possible to kick off a task and return it back to the caller. So awaiting is, when we have this capability awaits, this opt-in, that is, I will interleave. Like, I have the possibility to stop execution and other tasks can interleave with me. The ability to spawn one off and not see it finish, that doesn't require capability. You're not interleaving a system. You're creating a task, and we call it async instead of task of T, but we have asyncs of T and results of T, and you can freely create those and return them back. It does, though, require a capability to do. If you want to spawn off, you do actually have to have it's a capability model for creating them. But we do have them. They're first class, and they are fairly represented. They are fairly heavily used in our system.
So just to make sure it's clear. So imagine in .NET if, async method, when you called an async method, at the call site, you get to decide one of two things. Am I awaiting it, or am I going to spawn a new task to run that code? And so in our system, that's basically all it is, right? We don't call it task.run, we call it async factory.run, but it's the same idea. And that's kind of the key to the execution model, because for the awaiting code, which we found in our system, you end up composing deep call stacks of things that are awaiting. And if you pay the cost of spawning a task at every frame, you end up with heap allocations all over the place. So the recognition is that most code actually does just await, or it does fork join or something, but these are all structured you can use the current stack to kind of execute that, and it's more efficient. Whereas the inefficient thing is saying, hey, run this asynchronously. And so we've pushed that decision up as high as we can in the call stack so that you can have deep call stacks of awaiting code, and it actually just acts, the compiler can optimize it as it would synchronous code. And that was kind of the key, I think, innovation that the async model had.
All right, and I'm going to go ahead and turn it over to Alex now. All right.
So I'm Aleks Bromfield. I've been at Microsoft for about 3.5 years. I'm working on Midori the whole time. So I probably don't know too many of you in the room, but I'm happy to have the chance to meet you. So I'm going to continue talking about the systems programming features for a bit. One big category of features that we're starting to add is features for stack allocation and scoping. We want to give programmers the tools to control the aliasing and lifetime of their values. We also want to make stack allocation and inline object allocation safe, easy, and common. So here's a basic example of how these features work. You can see we have a list allocation here. The val indicates that this is actually a stack allocation. There's no heap allocation here. You can then create an alias to this list, which we call scoped. And this represents the fact that this alias has a statically lexical scope rather than a dynamic extent. We also support, so you can see that you can call a contains method here, which can be annotated as scoped. In the same way that you can annotate a method as immutable or readable to say that it doesn't modify any state, you can mark the method as scoped to say that it doesn't capture any state, it only uses it. And in fact, we also support scoped delegates. You can mark a delegate as scoped to indicate that the delegate is only used, not captured. And for such delegates, we're able to stack allocate the display class as well. So the contains call here, all of this code is completely free of any heap allocations. First. So the question was, does this mean that all of the list elements are on the stack, or can there still be heap allocation inside the list? Scoped is a notion about values, not about object graphs. And so depending on how list is defined, there may be heap allocation underneath. I mean, the short answer is no. Async functions are capturing state by definition. They can persist state. We need to hold on to it. And so, in general, scope things are not carried on through. Yeah, the short answer is no. However, yes. The main difference is when you mark all your methods as await, you're indicating that they may block, they may have interleavings, and so you can call awaits methods, and block yourself. Have your methods await your own result. It's when you decide that you want to spawn a separate task to wait for the result. That's the point at which you can't capture scope things. Yeah. So this actually leads on to the next slide, which is we do in fact allow deterministic destruction. So types can define destructors, which are very different from C# destructors because they're not finalizers. They run when the object actually goes out of scope. So in this case, you imagine that you've defined a val type here. You define val secure data, and this is just something you want to zero out the memory when you're done with it. You can create a scoped alias. When this val data goes out of scope, the destructor is implicitly called. So in a sense, it's as if you defined it with using, in that as soon as the value goes away, the value is destructed. We just don't syntactically require you to write using, which also means that we don't give you the chance to get it wrong. And it's also important to note that if you create a scoped alias to a destructible type, we ensure that the scoped aliases are no longer available when the value has been destructed. No, in this case, assume that this was the method and that this was the end. When you reach the end of the method, data is gone out of scope, and so you call it a destructor. If this was not the end, for example, let's say you had reassigned data, for example. In that case, we would actually invalidate the scoped data alias. So the system enforces the lifetimes in two ways. The first is that the scoping rules are based, roughly speaking, on lexical scopes, such that if you had a scope data defined in a parent scope, you would not be allowed to say scope data equals data. The second is that we track the aliasing of these values. So if you create a scoped alias from some value in a local, and you reassign that local, then we invalidate the scoped aliases. And we also have rules for detecting if you try to create a scoped alias to something whose lifetime we can't be sure about because it's in a heap, then we reject that statically. So next I'm going to talk about the Midori M# error model. So the M# error model is designed to support the Midori error handling philosophy. In a sentence, the philosophy is make it easy to find bugs fast. In traditional systems such as .NET, the vast majority of error cases are reported using exceptions. The problem is exceptions are recoverable. In fact, we found that something about 90% of cases where people would use exceptions in .NET are for situations that programmers really shouldn't be recovering from and can't be recovering from. Things such as argument validation errors, null dereferences, array out of bounds, arithmetic overflow. Midori's philosophy is fail fast, give the developer a chance to get into debugger, find the root cause of this error, and fix it. The corollary of that is that we want to minimize dynamic and recoverable failures. A lot of times programmers write code thinking they handle these cases, but they're so rare that the code doesn't get tested and in fact doesn't actually work. We do support dynamic recoverable failures for cases like parsers, and I will talk about those later. So, yep. Yeah, we definitely don't allow you to recover from Stack Overflow.
One thing Jared kind of glossed over earlier is that we actually compile the system with linked stacks. And that's key to the coroutines model to ensuring that they're lightweight. So we start with a tiny stack segment, and then we can grow it a bit more and a bit more and a bit more. And so what that essentially means is that Stack Overflow turns into out of memory, which is a fail-fast condition in the system.
And so again, another corollary of having so on desktops, yes, primarily and servers, 64-bit. However, we also run extensively on ARM. Yeah. No. So one. Yeah, so another corollary of minimizing dynamic and recoverable errors is that most code we know doesn't throw. The compiler is able to optimize it. We can avoid exception handling and exception table bloat. So the model I'm going to present, we've tried a number of different models over the past 3 years. Where we've landed now, it's been stable for about a year. It's been well received by the team, and it seems to be working well in practice. So we've divided errors into two cases. We have what we call internally recoverable and externally recoverable. So externally recoverable means things like the bugs we talked about, null dereferences, out of memory, things that a program can't handle itself, but someone at a higher level, someone debugging a program, a remote server would want to handle. And then the other type are internally recoverable, which are things like exceptions. If you're writing a parser, you want to be able to say, if I get a syntax error, I want to handle that error. So basically, we have errors. They divide into those two categories. And one of those categories is exceptions. Yeah. Yes. So in general, I'll explain let me explain our exception model first, and then that may answer your question. So here's an example of our contract model. And this shows most of the ways that tools that we give programmers to help find bugs. And in fact, contract violations are by far the most common category of these externally recoverable errors. So we have a concept in our system called abandonment, which basically means the process immediately terminates. We've gone through great lengths to make sure that when a process abandons, we preserve as much state as possible so that you can find out exactly what went wrong and why. So the most basic tools that we give programmers are requires and ensures. Requires is a precondition, ensures is a postcondition. If you've used .NET code contracts, it should look very similar. The main difference, of course, is that we've given language syntax for it. We also provide in postconditions, we provide the return keyword, which refers to any return value that the method might have. All preconditions are always checked on method entry. All postconditions are always checked on method exit and at all exits. We have no conditional compilation modes. Contracts are treated as part of the type signature. No, in that case, we've specifically designed the system to be amenable to static analysis. In fact, we've found a number of cases where postconditions especially can be very easy to prove statically and to a line. Yes. So we have our backend compilers, Bartok and Phoenix, have very good static analysis and interprocedural analysis frameworks, and we're using them and improving them to get better code gen around contracts. Yeah. So the question is, can you use contracts on abstract things without bodies, delegates, interfaces, and the answer is yes, you can. So semantically, the guarantee we give you is that when format is called, we know the preconditions are true. The implementation, in fact, the way this is compiled in the IL, which is how any third-party consumer would interact with this, we specify the contracts in a declarative way, and it's the job of the backend compiler to insert those checks. We've tried a bunch of different strategies and are exploring more, but certainly the generating checks at the call site is one possible strategy. Another one we've looked at is having 2 entry points for the method so that trusted callers can bypass it without having the code bloat of copying the contracts at all sites. Essentially, yeah. So the question was, can this system support other languages? The contract language compiles down to a declarative IL specification. Any other language that wants to can also generate this specification. At this time, we have no plans to support other languages in Midori, but it is possible. Yeah. Was there another question? Okay. So that's preconditions, postconditions. As people probably figured out by now, this is a virtual method. We enforce that contracts on overrides are the same as whatever it's overriding. We use the requires base and ensures base syntax to indicate that contracts are being inherited. We also support assertions, just like .NET. We have debug.assert. We also have release.assert for release mode checks. There's a few other things I want to point out which aren't immediately clear from the code because this shows correct code. So the question was, can a drive method have stricter checks? By subtyping rules, the sound thing to do would be to allow methods to weaken preconditions or to strengthen postconditions. We've designed the language support that would be involved in this. However, we haven't yet implemented it, partly because we're not sure that the complexity is worth it. I admit I'm not quite sure what you mean, but I believe the answer is no. We assume that, in fact, we very much hope that any expression within a contract is never going to fail. Yeah, so I mean, you can call whatever you want. You can use delegates. You can call a method that has contracts, but you can't express a contract about the contract method. So Jared mentioned earlier in the TEC section that we enforce side effect freedom of contracts. So in fact, for any expression in a contract or in an assertion, we check that that expression is not allowed to refer to any mutable state from the outside program. It's important to note this is for external state. So a contract predicate is allowed to create its own state and mutate that however it wants. But we enforce that these contracts cannot have any semantically visible side effect in a program other than making it a bit slower. And users who want to define their own assertions can opt into this behavior for themselves. Second, in the same way that C# will enforce that the return type of a method is at least as visible as the method itself, we enforce that for any members referred to within a contract body. The total of all of these things when we put all these things together, what we end up with is a very declarative contract language that still looks and feels exactly like the C# expression language. So we can take these contracts, in addition to checking them, we can put them in documentation, we can put them on MSDN, we can put them in IntelliSense. So we can use this as a tool to help users understand their APIs, in addition to simply making sure that checking them at compile or runtime. So we're not planning to. I can try to give you the 10-second version because we're running low on time. The basic idea is that a process is a discrete unit of computation with its own heap. So if a contract fails, then we assume that anything that could be sharing memory with that state has been corrupted and should be terminated. If you have an external agent which you don't share memory with, then that can keep running.
Hierarchical, so it depends on the level of isolation that you want. So if you want failure isolation, we don't guarantee that, we don't have sub-process failure isolation and reliability and resource management accounting. So you can think of what we call them near and far processes. So you can think of a near process as something that TSE guarantees the isolation. It's kind of an isolated object graph. It can have an interface. You can do message passing with it. But if that thing abandons, because the abandonment may represent some corrupt state that's global to the process, we rip the process down, which includes kind of these fine-grained processes as well. So the OS notion of a process is this coarse-grained thing. And so if you want strong isolation, you use the coarse-grained OS processes. You can think of the fine-grained processes that TSE enforces isolation for. And the programming model looks very similar. It's really just a dial that the developer gets to choose. So we should actually probably talk offline because it's interesting. We do have an IDL language for describing the interfaces between processes, and that IDL language actually can use contracts. It's written in M#, and you can actually annotate it with contracts. It's just enforced differently because you don't want the server process to abandon because an evil client came along and violated the contract. So the client is actually doing the checking. The server dynamically checks before dispatching a message to make sure that the message payload actually obeys the contracts. If it doesn't, it slams the connection shut to protect itself against kind of evil clients. But we should talk offline because we have a lot of interesting stuff there.
So any more questions on contracts? Yeah, so the question was, can we prove that these contract predicates terminate? And the answer is, of course, no. So we also cannot prove that they don't have bugs, that they don't abandon themselves. So it's not perfect, but we're able to rule out a large category of bugs. We can say that if your contract isn't terribly written, then if your program's able to run at all, then it will probably it mean the right thing with a much greater certainty than you can get if we didn't do these checks. Question is, have we been using contracts to generate automated tests? No, we haven't. However, with the declarative contract language, it's definitely something that we could explore doing in the future. So, as I mentioned, we also have support for recoverable errors, which we use exceptions for. We've got one of the biggest differences from us in .NET and traditional systems is that methods cannot throw by default. This is great for a few reasons. It is great for predictability because it means that when you call a method, you don't have to worry about some hidden exceptional case. It also provides great code quality. Bartok and Phoenix are able to optimize code much better, knowing that there's fewer exit points and no exception handling needed. In fact, we've checked our source base, and over something about 85 to 90% or more of the methods in our code don't throw. Now, what we say is if a method can throw, then the method itself and any of its callers need to opt in to declare that they know about the throwing. And this is great for reading code because you don't have to understand what a method does. You just look at your source code and you know whether or not it throws. So here's a simple example. If you try to write some code and you write a parse method and you say, okay, I'm going to throw an exception, you'll actually get an error. And so what you need to do is you add the throws keyword to your method, and that indicates it's allowed to throw. Now someone else who's calling your method, they're going to get an error because they also need to opt in and say, I might need to be aware that I'm throwing an exception. And so what they do is they write try to indicate they're trying to run this method. And they also have to mark themselves as throws. So the question is, how does this interact with generics? Are you referring to delegates or to... we have quite a few places in our system where we need to be, essentially polymorphic on throws or not. What we do depends on the system. In quite a few situations, we actually just don't allow throwing at all because it turns out we don't need to. The cases where we do, sometimes we just say the method is throwing, and sometimes we'll offer two versions of a type, the throws version and the non-throws version. So one more thing. And so we've certainly talked about, we know that there's places where it would be nice to be able to write something that's kind of, polymorphic on whether or not something throws. We haven't yet found a design there that meets the sniff test. Basically, we don't, we can very quickly get into, research like stuff that just isn't going to make sense to anybody. But it's something that we definitely will continue to explore. And if we find that, like a dead-on simple solution, we'll happily take it. So the question is, I believe your question is, can you catch exceptions? Or yeah, so okay, so I think we missed a slide somewhere. But yes, you are in fact able to catch exceptions. Its syntax is basically the same as .NET. There's one important difference, which is that the exceptions you're allowed to catch are determined based on static information. So in this case, we show if you have a method that throws, it doesn't matter what exception type you actually throw. The only thing that you're allowed to catch, we treat this call as if it was able to throw types, anything that derives from system.exception. And so when you try to call this here, we're going to say, sorry, we haven't handled this. Yeah, so if you want to be able to throw a derived exception type, we allow you to say only throws to indicate the types you want to throw. In practice, we've found so far that most methods that fail for one reason. And so by far, most of the methods in our system only throw a single exception type. We've also found, again, that the majority of our methods don't throw. So we're at about 10% of the methods in our system throw, and maybe about 10% of those methods throw something other than exception or other than a single type. So the nightmare of Java checked exceptions where you have these like 10 exception lists and you've got to handle all of these, we just don't see that in our system. And we have no reason to believe we will. So in the current model, you are in fact allowed to list multiple types if you want to. In the model, you can list multiple types. Listing a single one is very common.
Just to clarify, you can, so if you, in the previous slide, if you caught the exception, you'd still have to say try when you call the method. You wouldn't have to annotate your method throws. I hope that part's clear. You can throw derived exceptions. So if you want to include any amount of diagnostics information about the failure, feel free, go ahead, implement your subclass. What you can't do is then, as a caller, depend dynamically on the fact that you know that method throws a particular exception type. That personally has always bugged me about kind of the way exceptions work today. It's very dynamic, right? You have to kind of know, well, this thing happens to throw a foo exception. And then the next release comes out and somebody changes it to throw a bar exception, and that's a breaking change, and yet the compiler doesn't enforce that. So what only throws does is it bakes that part into the contract. So if I threw my exception, or say I threw foo exception and bar exception, I could either say just throws, and my caller can't depend on those exception types. I can say throws plus only throws, foo exception, comma, bar exception, and then I'm forever locked in to never throwing anything other than foo exception and bar exception. You can throw a subtype, and what you can do is, Christoph actually wrote, I think you call these open exceptions. So you can leave it open for future versioning. So you could say only throws foo exception, comma, bar exception, comma, exception. Now you can add to that list indefinitely going down the road, but of course a caller who only catches foo exception has to worry about the fact that there are other exception types, and if they don't have a catch-all handler, they have to propagate whatever remains. There's definitely, like the speech code base is kind of what I consider to be third-party code, and it's definitely composable. Sometimes you pass in, I've implemented an interface, or I have a delegate that I'm passing into an extensibility point. I would say the common case for only throws actually very seldom leaks out into public APIs. A lot of time it's for an internal implementation of a large complex system like the JavaScript engine or a reactive framework. For example, a reactive framework, it may need to abort to restart the calculation. And it actually uses only throws for that, but it's not something that programmers really need to worry about. It's just how it internally implements things in a way that it's statically type checked. So I actually, exceptions are rare in the system. The 10% out of all the error cases. I think this is like 0.5% at most.
I mean, certainly we found that many APIs, which in other systems would return a derived type, throw IO exception, found exception. In our case, they just need to throw exception because there's only one way that API can fail. So yeah, we found that it's much less likely to need derived exception types for that, and by far the most common case is throw exception. Sure. So the question was, how do you handle cases like a delegate where you might have methods that throw different exception types? The answer is you just throw exception. We don't support that kind of higher order polymorphism over exception types. Not over 5 different types. Okay. Yeah. No, this is it for. Yep.
So why don't I just quickly wrap up, and then we'll take all the questions. Basically, we're trying to finish the language, so anything not in the slide deck, this is kind of useful exercise because I actually have to deliver a V1 plan for the language 2 weeks from now, so this actually talk helped me prepare for that. So the big one that we have a design written up and that we're pretty confident in, there's still some very tricky aspects of it, is non-null types. So we think that non-null types are a big enough bet. It's the kind of thing that you can't add in V2 of the language. It's high enough value. In fact, we actually, have only had null reference bugs in the speech code in terms of like finding live site issues. And so I really want to fix this one for good. So we're going to try to do non-null types. We have until July to implement them and at least partially deploy them. So that'll be interesting. But if anybody who's interested, we do have a design doc. You can read it. Love feedback on it. The obvious tricky areas are generics, arrays, zero initialized structs. We think we have good answers for those. Changing the defaults, as Jared mentioned, again, this is one of those things you can only do it once. It's going to be tricky, but things like read-only fields as the default is definitely on the list. Sealed classes by default, so you actually have to explicitly opt in to having extensible classes. By value capture and delegates. We commonly find that by ref as a default, like think of the loop induction to variable problem. We think that's a big enough bet to make. Readable is the default for references, although this is fairly controversial because the more of these we add, the more ML-ish C# starts to feel. So one of the great things I find in the system is that we've kind of struck a nice balance between functional programming and imperative programming. You still have for loops. You can still have, you can have string builders that you build up and mutate things. It feels kind of natural. I do personally fear that the further down this path we go, the further away from C# we get. So we're going to tread lightly here for sure. There's a lot of other small features. In fact, we didn't mention a bunch of the features in the language, especially interaction with the framework. Like we've, redesigned IEnumerable, so you don't need 2 calls to get the item out of it, and like a bunch of small things like that. There's definitely a lot of syntactic sugar we need. First class void in generics. Aleks has already implemented this. We basically just need to test it and check it in. So there's a long list of small things. The V1 plan is going to be published on the Midori website, so anybody who wants to kind of review that would absolutely love the peer review. Developing guidance for using the features and make sure Midori is actually consistent and using the features as a showcase platform is on the list as well. And despite it appearing that we have a lot of work, we have an enormous cut list. Anything that didn't really strongly strengthen one of our core principles, we kind of had to put on the cut list. So, for example, tuples, and there's quite a few things. So we're only tackling the game changers and things that we had in flight. So it's really time to kind of focus and finish. So wrapping up, I think it's really exciting. Midori is now in production, actually delivering customer value, saving money for Bing, and obviously we're going to try to kind of increase that over the coming years. I think this year we're going to look for another Bing workload or a couple. At some point, I think expect Midori to be more self-serve, and we'll have a website where people can go and download SDKs and use the stuff. At this point, we're kind of helping our partners along because we think it's an important to get the relationship off on the right foot. We do have some more things to come. So I'm giving a MSR talk in March, which is more of a top-down, very high-level overview of Midori. The hope is to actually spark a lot of collaboration across MSR and to go, to start going deep on some of the other areas. We have a record-based file system, and we have a lot of interesting aspects of the system that could, partnership with research would be great. And of course, we always have positions for great people who like to code. I wouldn't be doing my job if I didn't have that plug in there. And feedback's definitely appreciated. So we did actually publish a paper on the TSE stuff in OOPSLA. It's about 2 generics revisions behind at this point, but still kind of useful. And of course, we have all of our design docs are on the website. You can listen to the code, try it out. We'd love to hear your feedback. So with that, turn it around to Q&A.